Hi, welcome back to Mathematical Logic. In this video, we're going to talk about mathematical proofs. So up to now, we've been talking about using these techniques, for example, the tabular tree method, inference rules, to derive conclusion. But we only have kind of relied on the syntax and semantics of propositional logic and first-order logic. We didn't really apply any interpretation to them. And so in this video, we're going to introduce some common interpretation and domains, and then common proof techniques that we use in basic introductory mathematics. I know we have some math majors in the class, and even computer science major who probably can use some of these ideas in their other classes. So here's some common domains in mathematics. Sometimes we refer to the counting numbers 1, 2, 3, all the way up to as big as you want. This is the infinite set, and we use the n to denote the counting numbers or the natural numbers. Z is a set of integers, basically the counting numbers 0 and also all of its negatives. Q is the set of rational numbers, instead of p over q, where p and q are integers and q is non-zero. And then the real numbers, set of all real numbers. So here's some examples of well-formed formulas of first-order logic in a mathematical interpretation or context. We're going to assume that the domain of these examples is the real numbers. So for example, here's a well-formed formula. X is less than or equal to 5 and x is greater than 3. So notice that this well-formed formula in first-order logic has a free variable. X is a free variable. And this statement is true for some for x, and it might be false for others. For example, when x is 4, 4 is certainly less than or equal to 5 and bigger than 3. So when x is 4, this is a true statement. But if x is 10, this is a false statement, because the variable x is free. And then here's another well-formed formula. So for all x, x is less than or equal to 5 and x is greater than 3. So again, x here is in the scope of the for all x. So this is a bound variable. It's not free. And this is a closed sentence, and we can say this sentence actually is false, because it's not true that for all x, if the domain is the set of all real numbers, then it's not true that every x is between 5 and 3. For all x, x squared is greater than or equal to 0. This is true, right? For all x, if you square it, it's bigger than or equal to 0. So this is true for all x in the domain. And then for all x, for all y, x plus y is y plus x. So this is a property of addition called the commutative law of addition. And this is true for all x, for all y in the domain. And so this is a true statement. It's a closed sentence where x and y are both bound. Okay, here's another example. There exists an x such that x is greater than or equal to x squared. This is true because if all we need to show that this is true is to come up with one example, and that is 0. 0 is certainly bigger than or equal to 0. But there's actually many other examples, infinitely many examples. In fact, another easy example is 1, for example. Here's another example. There exists an x such that x is less than 0 and x squared equal to 1. This is true, for example, when x is negative 1. So these are examples of first-order logic statements that are in this context of the real numbers and basic operations with the real numbers. I want to introduce some definitions that will be helpful for us when we discuss some basic math proofs. So even versus odd. An integer x is even if there's an integer y so that x is 2 times y. An integer x is odd if there's an integer y such that x is 2y plus 1. So those are the definitions of even and odd. So here's an example of first-order logic model. The domain is integers, and ex is a predicate with one argument, where ex means that x is even, ox means x is odd. These are predicates with one argument. Here's a function, s of x is x times x plus 1. This is a function with one argument. It takes something in the domain and it gives you something else in the domain. And then here's an example of a well-formed formula in this model. For all x, x times x plus 1 is even. And we can write this in first order or predicate logic by saying this: for all x, e of s of x. Okay, prime numbers. if n is not 0, let's talk about what it means to divide an integer to divide another integer. So suppose n is not 0 and a, both of these are integers. We say that n divides a. The notation is n vertical line a. If there's another integer m, so that n times m times n is a. In other words, n is the divisor of a. We can also say that a is a multiple of n. So maybe I should give an example. So I forgot to do an example here. So for example, 3 divides 9, for example, or let's do 12, since we have that 12 is equal to 3 times 4. So that would be an example of okay, so an integer p, which is positive, is a prime if it has exactly 2 positive divisors, namely 1 and itself. Now if a is bigger than 0 and has more than 2 positive divisors, if it has more than 2, then we say that a is composite. And by the way, 1 is not prime, and 1 also is not composite. So there's actually many theorems about primes that are really amazing. Some of them are really hard to prove, and there's also many questions involving primes that are very easy to state but very hard to prove. Again, there's a whole branch called number theory that deal with primes and divisibilities. So one simple example is a famous example called the twin primes theorem. Well, it's conjecture really at this point. We don't know if it's true, but it's likely to be true because computers have checked for really big numbers. But it says that there's twin primes are basically primes that are consecutive, that are in the form p and p plus 2. For example, 5 and 7 are twin primes. They're next to each other. 11 and 13. And the conjecture says that, oh well, are there a lot of there are an infinite number of these. So let me move this up so you can see the rest of that. And so the conjecture says that there's actually an infinite number of these twin primes, but no one has been able to prove it. But computers have been able to check a lot of numbers up to a very high value, but we still don't have a proof of this conjecture. Rational versus irrational. A real number x is rational if there's integers at p and q such that p divided by q is x, and otherwise it's irrational. For example, pi or root of 2. These cannot be expressed as a quotient of 2 integers. If x is irrational, here's the statement: if x is irrational and y is rational, the sum is also irrational. So we can write this in predicate in first order logic as for r x for r y. X is irrational and y is irrational. Y is rational implies that x plus y is irrational. I think this is a question that we're going to prove in one of the homework. In fact, we might prove it later in the class, later in this lecture. Okay, so many statements in mathematics formulated, many theorems rather, are formulated using logical entailment. And so, for example, we might say something like this: assume P, we want to prove Q, or equivalently, P implies Q. Or sometimes we might have several assumptions: P1, P2, all the way to Pn. This logically implies S, or equivalently, P1 and P2 and all the way to Pn implies S. So these are kind of different ways to formulate mathematical theorems. So the sentences on the left, so these, for example, these are called the premises or the givens, and then S is the conclusion. So for example, if a function f is differentiable, is continuous, assuming that fx is differential, we can prove that fx is continuous. So this is a theorem in calculus. Given a statement of the form P implies Q, we have a bunch of statements that we can generate from this. If I flip the order and negate both of them, not Q implies not P, this is called the contrapositive. The converse is just flipping the order, Q implies P. The inverse is flipping P and Q but preserving the order, not P implies not Q. So it turns out in one of our homework we proved that a form and its contrapositive is equivalent. In other words, they have the same truth table. So for example, if P implies Q is equivalent to not P, Q imply not P. So if one is true, then the other is true, and then if one is false, the other is false. So this will be useful, that we'll see later. This will be useful when we talk about some mathematical proofs. So here's some mathematical proofs that are common in basic math. So one of them, the first one is called direct proof. We'll go to each of these in details later. Existence proof, uniqueness proofs, indirect proofs. There's actually two kinds. One of them is called proof by contradiction, and proof of the contrapositive. So let's go through each of these proof techniques. So direct proof. What is a direct proof? Direct proof is basically a sequence of statements where each statement is either a given or a premise or a deduction from the previous statements. So this is what we have seen when we do the inference rules previously. We've done direct proofs. And the last statement is the conclusion that we want to prove. So the use of variables is actually very important in mathematical proofs, or really any first order proof. Their improper use can result in unclear and even incorrect arguments. So every variable in a proof has a quantifier associated with it. Again, there's two types of quantifiers that we saw in first order logic, whether it's universally quantify or existentially quantify. And sometimes when you write math proofs, sometimes these are kind of implicit. So I'll show you an example in a second where I'll explain explicitly how variables are quantified. But for the most part, it's okay in our homework that we don't explicitly, clarify everything if it's clear. So we can explicitly quantify every variable in our proof, but if it's clear from context, it's okay that we don't always explicitly state it, but every variable has an associated quantifier. Okay, so a universally quantified variable is introduced when we try and prove something like for all x, p of x implies q of x. And so the language we usually use in math to do something like this is to say, suppose that x satisfies p of x. Suppose that we have an arbitrary x, meaning for any x. Or we can also say something like assume p of x, or let p of x be true. So these are different ways that we say in math to kind of begin to prove something like this. And then assuming p of x, we want to prove q of x. But when we introduce an accidental quantified variable, it's usually defined in terms of other things that have already been introduced in the argument. In other words, that the x that we introduce accidentally usually depends on the previous mentioned variables or quantities in the proof. So let's see some example of this. Here's an example. Assume that the domain is a set of integers. We want to prove that if n is even, so is n squared. In other words, for all n is even implies n squared is even. So here's a proof, and we'll be explicit about some of these quantifier. Okay, so assume n is even. So n is any arbitrary even number. So this is basically n is a universally quantified variable, right? This is we're trying to follow this quantifier here, the for all quantifier. Because n is even, we can write n is equal to 2k for some k by definition. And notice k is an existentially quantified variable. It's defined in terms of n. Because n is even, there exists a k, so that n is 2k. Notice, right? This is so there exists a k here. So again, in your proof, in your homework, you don't have to explicitly say everything like this, but this is the first time we're doing this, so I want to be clear about that variables here in mathematical proofs are either quantified universally or existentially. And so n is 2k, so n squared is 4k squared, which is 2 times 2k squared. Again, this is a bunch of equation here, and this is essentially using these algebraic manipulation are basic examples of modus ponens, right? If n is 2k, then certainly n squared is 2k squared, etc., etc. So this is using conditional elimination or modus ponens. Again, this example were explicit here, but later I won't explain some of these things. I noticed that if I let j be 2k squared, so in other words, and make this be j. Again, j is existentially quantified, defined in terms of k. So j defined in terms of k, and this says that n squared is 2j, so that n squared is even by definition. So this is a kind of a standard, number theory proof in math, and number theory is very simple and allow us to kind of see examples of how to prove this in a context of a certain interpretation. In this case, a number theoretic interpretation. Okay, another kind of proof is existence proofs, and these are actually very important theorems in math. So we try to prove that there exists an x p of x. In other words, there's an object x that satisfies some formula p. So in existence proofs, we want to be as specific as possible. I think the most satisfying and useful existence proofs are the ones where you give a specific concrete example, or at least describe how to explicitly produce such an x. So for example, if I want to prove that there's a prime p such that p plus 2 and p plus 6 are also prime, then to prove that there exists such a prime, I come up with one example. So for example, when p is 5, 5 plus 2 is 7, 5 plus 6 is 11, these are primes. So this is a proof that this statement is true, because we prove by producing an example. By the way, 5 is not the only proof, the only answer. 11 also satisfies this. In fact, this is a famous unsolved problem, again unproven, that there's infinitely many primes that work. In other words, there's infinitely many primes that p plus 2 and p plus 6 are also primes. So this is very similar to the twin primes conjecture. Counter example. This is actually a slight variation of the existence proof. We disprove something by counter example. Suppose that we're trying to prove something like this for all x p of x. Well, one way to maybe disprove this is to come up with an example that shows that this is not true. And so we want to, if I negate this, we want to negate this to show that we can negate this by using de Boer's law, right? To show that this is not true. We just bring in the negation. We saw this in first order logic. So this is equivalent to there's an x such that p is not true, right? In other words, if it's not true that for all x p of x, then certainly there's one x so that p of x is not true. And so finding a specific x satisfying not p of x is called a counterexample. And this counterexample is a counterexample to the assertion that for all x p of x. So for example, here's a statement for all x. 6x is even implies that x is even. If I want to disprove this, we can come up with one example so that this is not true. And so, for example, here's the counterexample. If x is 3, then 6 times 3 is even, but 3 is not even. So this would be a counterexample. Another way to think about this is that another way to find a counterexample is to take the statement and we just negate it, find the negation of the statement. And so to prove that the original statement is false, we negate it and prove that the negation is true. So to negate this, right, when I negate the for all, it becomes there exists. If I negate a conditional, it becomes, so if A implies B, the negation of that is A and not B. So the negation of this is there exists an x such that 6x is even and x is not even. So if I can find one example of this that makes this true, then I found a counterexample to the original statement. So again, the example of the negation is a counterexample of the original, right? So you want to think about that. So again, 3 is an example of this statement being true. 3 times 6 is even, but 3 is not even. Okay, so occasionally so it's sometimes not possible to find a specific example, and so so sometimes an existence proof sometimes may be constructed indirectly or by using other existence results. And so let's show you an example from calculus. Again, you don't need to know calculus for this, but if you understand calculus, this might be a helpful example. We want to show that there's a solution to this equation, x cubed plus 3x minus 2 is 0 in the interval from 0 to 1. We want to show that there exists such a solution without producing it. Again, one way to do this is to actually produce a solution. In other words, solve this equation, then you have proved the existence proof. But maybe that's not possible. Maybe solving this is hard, so we want to find another example of proving this without producing an example. So this is an indirect way to prove an existence proof. So we actually use other existence results. So for example, here's one way to do it. Since this function is continuous, and if you plug in 0, you get -2, you plug in 1, you get 2, so you get a negative result and a positive result, there's a theorem in calculus called the intermediate value theorem that says that if a function is continuous, it actually has to go through all the values between these two values, and 0 is between -2 and 2. Therefore, a continuous function cannot skip through 0. Therefore, there is an x that makes it equal to 0. So again, if you don't understand that, that's fine. But if you've done some pre-calculus, some calculus, so this is an example where I prove that there exists an x in this interval, but I didn't explicitly produce it. I just say that I used another theorem called the intermediate value theorem to produce the existence of such a solution without explicitly produce it. So this is an indirect way to do this proof. Sometimes we have a mixed quantifier for the existence argument. So for example, we might have for all x there exists a y. So this is a little bit more complicated, but this is basically trying to do many existence argument at the same time. So for any given x, we have to prove the existence of a y for that given x. So this is doing existence proof for every possible x in the domain. And so for any value of x, we'd like to construct a y that makes p of xy true. So for example, there's no largest integer. So this is an example of something like this. I can write this as for all n, there exists an m such that n is less than m. Right? So any integer, you forgive me, I can find something bigger so that there's no largest integer. So here's one way to prove that, to prove something that's a mixed quantifier like this. Suppose the n is given. In other words, n is arbitrary for any n. Well, here's how you can produce an m that depends on that n. Let m be n plus 1. So we take any given n, add 1 to it. We found an m that is bigger than n, because n is less than n plus 1 certainly, and n plus 1 is m. So this is an example where we're proving existing argument for an infinite number, possibly of other value of x. So given any n, we found something that satisfies that condition. Okay, how about uniqueness proofs? So existing and uniqueness proofs, sometimes they go together. We want to say that there exists an object that satisfies something, but this is the only object that satisfies that property. So here's a symbol that we use in math, this explanation that says that there is an x and is the only x. So there exists a unique x that satisfies p of x. Or there's exactly one x such that p of x. And so for example, here's the universe, here's the all real numbers. There exists a unique x such that x squared plus 1 is 2x. So this is true since x1 is, first of all, it's a solution. If you plug in 1, you get 2 is equal to 2. But it turns out that you can also prove that it's the only solution. In other words, there's no other solution except for x is 1. And again, this is kind of beyond the scope of this class, but from calculus, if you use the mean value theorem, it turns out you can prove that x is equal to 1 is the only solution. So the key is that sometimes it's very hard to prove uniqueness, and you might have to rely on other theorems to be able to prove it. So the quantifier, there exists a unique x. This one you can really break it down to two parts: the existence part and also the uniqueness part. In other words, there exists a unique x such that p of x is the same thing as saying there is an x such that p of x, and for all x, for all y, if we have px and py, well, that implies that x is equal to y. In other words, if you have there first has to be at least an x that satisfies p of x, and whenever you find two things that satisfies this property, it turns out to be the same thing. So that's the uniqueness part, the second part here. So sometimes you find that it's really impossible or difficult to prove something directly, but it's at least maybe easier or at least possible to prove something indirectly. And so there are two methods of indirect proof: the proof of the contrapositive and proof by contradiction. So these are closely related, and sometimes they're interchangeable in some circumstances, although the proof by contradiction is more powerful. What they have in common is that they both assume the denial or the negation of the conclusion. So here's the proof of the contrapositive. If you have a statement P implies Q and you want to prove it, the contrapositive form is not Q implies not P. For example, if it's Sunday, I go to church, the contrapositive is if I'm not going to church, then it is not Sunday. And so we saw earlier in the lecture that that really any sentence and its contrapositive are equivalent. In other words, they have the same truth table, and so sometimes it's easier to prove the contrapositive than it is to prove the original statement. So here's an example. Suppose that n is positive, and we have that 4 to the n minus 1 is prime. We want to prove that n is odd. If I try to prove this directly by assuming that 4 to the n minus 1 is prime, and using that fact to prove that n is odd, it's actually very hard. You should try it and see if you can do it. But if I rewrite this in its contrapositive form, like this, again negating the conclusion if n is even, and then 4n to minus 1 is not prime. So that's the contrapositive. So this statement is equivalent to the original, but it's much easier to prove. In fact, let's prove it now. So assume that n is even. That means n is 2k for some k. 4 to the n minus 1 is 4 to the 2k minus 1. This thing can be factored into 4k minus 1 and 4 to the k plus 1. And so that says that 4 to the n minus 1 is factorable into two factors. So now we have to prove that these two factors are actually bigger than 1. Now because n is even and n is positive, we know that n is at least 2, and you plug in n for being at least 2, we see that these terms are bigger than 1. And that says that we can factor this term. That means that it's not prime. And finally, the last technique is called proof by contradiction. To prove a sentence P by contradiction, we assume not P and derive some kind of contradiction to a statement that is false, and this implies that P must be true. So suppose we try to prove P implies Q, then we assume P, and then we assume the negation of Q. In other words, we assume that Q is false, and then we try to get a contradiction, and then if we get the contradiction, then we have proven the original statement. And notice that the contradiction might not be not P. In fact, this is the principal difference between proof by contradiction and proof of the contrapositive. In the proof of the contrapositive, we assume that Q is false and try to prove that P is false. But in the proof by contradiction, we assume P and assume not Q, and then try to get any contradiction. It doesn't have to be the contradiction of P, it could be any contradiction. For example, if x is irrational and y is rational, we want to prove that x plus y is irrational. So let's do a proof by contradiction. Again, we're going to start by assuming the assumption as usual, x is irrational and y is rational. Then we're going to assume the negation of the conclusion, which is that x plus y is rational. And notice that the power behind is that by assuming the negation of the conclusion, we have an extra assumption that gives us more information to prove what we want, or at least to get the contradiction. So because our assumption that x plus y is rational means that you can write it as p over q. We also know that y is rational, so that's m over n for some mn integers. And so the trick here is to write x as x plus y minus y. Notice these cancels to give you x. The reason why we want to do that is because x plus y we know can be written as a fraction, y can be written as a fraction. We can subtract those to get another fraction that proves that x is rational. But we saw earlier that x was assumed to be irrational. So there's the contradiction. It cannot be both rational and irrational. So that's the contradiction, says that x plus y must have been irrational. Otherwise we get that contradiction. Okay, that's it. Thanks for watching.